everyone, welcome to APS Deep Academy and this is your mentor Swati Joshi. In this class, we will study formation of holes and electron-hole pair, the process of recombination, mobility and conductivity, and drift and diffusion currents. Okay, now let us begin with today's class. I am drawing a simple structure of energy diagram of silicon. We know that silicon has atomic number 14. This is shell 1, this is shell 2, this is shell 3, now valence band and conduction band. In vertical axis we have energy. See here, in first shell we have 2 electrons. In second shell we have 8 electrons. In third shell we have 4 electrons. Third shell is also considered our valence band, and above this we have conduction band, and between valence band and conduction band we have energy band gap, which is easy. So this is the basic energy structure of silicon. Now here what is happening? See another diagram of valence band and conduction band. See, in valence band we have 4 electrons. Conduction band is till now empty and this is Eg. What is happening here? Even at room temperature, this is the structure of intrinsic semiconductor. We didn't do any doping here. So this is the simple structure of intrinsic silicon crystal. Now what is happening here? Even at room temperature, this silicon crystal has sufficient heat energy to mobilize its electron, or electron start vibrating or start jumping towards the conduction band even at room temperature. Okay, here are two things I have to mention. One is room temperature, another one is 0 degree Kelvin. So at 0 degree Kelvin, it means where no heat is there, 0 degree Kelvin, which is minus 273 degrees centigrade. In this condition, intrinsic semiconductor behave as insulator because no free electron in valence band who wants to take part in conduction. But if it has sufficient heat energy at room temperature, which is 27 degrees centigrade or above. So at this temperature, this electron has some energy so that it want to leave its shell and take part in conduction and move to conduction band and place here. Now, in this space where the electron left, a vacancy is created. Let's say this is the vacancy. So electron left and this is the empty space here created. This empty space is called as hole. So when this electron jump into conduction band, even at room temperature, he has sufficient heat energy to go there. So we can see that heat energy. Okay, heat. Electron is exciting due to heat. Okay, now in this space, one hole is created. So this is the formation of electron and hole pair. EH pair. This is the EH pair. Electron negative, hole positive. So this is our EH pair. What happened? Recombination occurs when a conduction band electron loses its energy. Okay. Now this electron doesn't have sufficient energy to take part in conduction because this is only at room temperature. We didn't give any electric field here. So at till few seconds or till few time, whenever it has sufficient energy to move around conduction band, it will stay in conduction band. But when it loses its energy, it again come back to the previous space of valence band. So this process is called recombination. So here again hole created and this electron loses energy and come back to the previous place of valence band. So this is the process of recombination. Recombination. Now here 2-3 terms we have to understand. Number one is intrinsic semiconductors behave like insulator at 0 degree Kelvin, and they have few charge carriers in conduction band. Even at room temperature, they have sufficient heat energy to jump from valence band to conduction band. And if this electron in conduction band loses its energy, it come back and fall into the valence band, then this process is called recombination. Okay. Now, I think you have understand what are energy band diagrams and what is the electron hole pair concept and what is the recombination process here. Now we will move forward to our next topic for today, which is mobility and conductivity. Okay, now we will discuss mobility and conductivity. Okay, now what is happening in a metal? Electrons are placed in a fashion that in room temperature they are vibrating, and due to this random motion or vibration they are cancelling each other's flow. So if there are few electrons in a unit area of a metal, they are flowing in randomly, they are flowing in randomly. So a particular flow of electron in a particular direction is not forming if we are not applying any kind of electric field. This is the position where the electrons are flowing randomly in a particular room temperature. So what is happening here? The electrons are cancelling each other's flow, and the speed or velocity of electrons to perform to flow in a particular direction is not achieving. So what we are doing, if we apply a constant electric field, let's say E volts per meter, what is happening when I apply a electric field in the metal, electron accelerate and the velocity was with increase with time. These electrons are accelerating. Now this motion is accelerating, and at a particular velocity they start flowing, and now they are flowing in a particular direction. So where electrons are moving, if I am connecting a battery here, then this is the positive terminal, this is the negative terminal. So electrons move towards positive terminal, means they are moving from negative to positive terminal. So this is the flow of current here from negative to positive terminal. Okay, now in this what is happening, they are continuously colliding, they are continuously losing their kinetic energy and doing cancelling each another, but still at a particular time when they all start moving in a particular time, they attain a particular velocity from which they start conduction. So this velocity is considered as drift velocity. What is happening here? Due to this collision and cancelling each other energy, losing kinetic energy, increasing kinetic energy, what is happening at a particular position? They are attaining at a steady state condition. They are attaining a speed which is called as drift velocity. Okay, now what is our drift velocity? We can see here drift velocity V is nothing but it is proportional to the electric field. Okay, it is proportional to the electric field which we are applying. So this is our drift velocity. Okay, now this, if I have to remove this proportionality constant, I have to put here mu. What is mu? Mu is the mobility here. What is mu? Mu is the mobility of electron. Now we have few terms to understand here. V is the velocity, drift velocity. Electron is achieving the drift velocity after applying the electric field, and they are coming into a particular steady state condition. Then they are attaining this velocity which is drift velocity, and this drift velocity is directly proportional to the electric field, and this drift velocity is considered as mu into E. Where mu is the mobility of the electron. Mobility means how this electron is moving. Mobility is a function in which we can see that how this electron is moving and from which magnitude the electron is moving. So there are few terms we have to understand. One is mu, which is mobility of electron. E is the applied electric field, and V is the drift velocity. So here we consider that if I apply a particular electric field to a metal plate, then a drift velocity is attained. Now I discuss drift velocity. I will also discuss what is drift current. Drift current is considered as J, which is nothing but NE into V. V we already know, V is our drift velocity, and this NE is what? This NE is our per cubic meter electrons. How many electrons are in per cube meter? Okay, if I have to calculate current in a particular system, particular metal, we don't have to calculate in the whole area. We have to calculate in a particular, like say in this area. So this area is considered as per unit area. So per unit area, how many electrons are there? N into E. N is the number of electron per cubic meter. Okay. So N into E into V is our drift current. V is our mu E. So if I put here whole term, then Ne mu E is our drift velocity. Okay, now we will discuss what is diffusion or what is diffusion current. Okay, if I have to talk the diffusion or the process of diffusion, it means I am considering semiconductor here, which is extrinsic in nature. Extrinsic semiconductor. So what is happening in extrinsic semiconductor? I am doping it with some electrons or holes. We know that n-type or p-type impurities. So there are few electrons and few holes. So electron has negative charge like this and holes are positive charge. So like this is ion type, majority charge carriers are electron. Let's consider. So what is happening here? Due to the potential gradient, positive and negative difference means how much potential is in negative charge and how much potential is in positive charge. Due to this positive gradient, the electron started flow from higher potential to negative potential. Here the negative potential or electron potential is high. So electrons start flowing in a particular direction, like negative to positive, means from electron to hole they are flowing. So this is the process of diffusion. What happening here? Due to the potential gradient which we create in this lattice, due to the process of doping, we increase some electrons or some holes, like this is n type, so we increase few electrons here. So due to this potential gradient created here, some electrons are more than holes, so they are flowing in a particular direction where they where higher potential to lower potential. So this is the process of diffusion. Now, if I now due to this diffusion, some current in the semiconductor is producing. So now we will discuss what is the current here. So J is our diffusion current. Diffusion current is nothing but E dN d by dx of nx. Let's understand this. E is nothing but charge of electron and dN is our diffusion coefficient. So we have to consider here dN is for n-type diffusion coefficient, and if I am doing it for holes, then we have dP diffusion coefficient. So this is the constant here. E is the electron, charge of electron, or how many electrons in this, and n or x, d by dx of nx. Here what is mean? At x per unit area, concentration gradient. Okay, in whole lattice or whole structure, we can't find the current. So we find a particular area, small single area, which is nothing but a differential of per unit area. Okay, the d by dx of per unit area, which is nx. X is nothing but per unit area. We are considering a particular element here, which is x, which is a particular unit area here. So we are calculating the diffusion current with the help of a diffusion coefficient and the differential of n into x, means how many electrons are in this particular area. So this is your basic formula of diffusion current here. So today we discuss what are mobility and conductivity. We also discuss formation of electron hole pair and recombination process, and we also discuss drift and diffusion currents. So this is all for today. Thank you.